Hi guys, let's talk a little bit more about solving systems of equations. So yesterday we spent some time working on solving systems of three linear equations, three unknowns, and we were really able to use our kind of prior knowledge techniques of substitution and elimination. So hopefully that didn't feel too crazy. A little bit more to keep track of for sure, but in terms of strategy, it paralleled so nicely with our knowledge from the past. So today we're going to actually look at nonlinear systems. So that means we're going to start getting some maybe parabolas or circles or something that's not just a linear thing on the page here. So I wanted to use Desmos, and then I'm going to follow up with some algebra on the screen too. But let's just graph a quadratic. So I'll just pick on y equals x squared minus 3, right? Just a nice quadratic equation. And let's choose to intersect that with something linear. Actually, I'll just make it something like y equals mx plus b so that we can look at a variety of examples together. So I want to explore what are the different possibilities when you have a parabola and a linear function. How many different types of solutions could you achieve? And maybe a nice way to do this is to just let first the slope change for you guys. So let's just watch the slope of the linear function change for a moment there. So as the slope changes, let me pause it at an instant here. Would you agree that there's still basically two places where we can see the linear function intersecting with the parabola? Even when the slope became negative, I'll slide it to the negative, right? We can still pick on two places where the linear function intersects with the parabola. So for sure, one option in solving this type of system would be to obtain two solutions. Okay, and that's going pretty high, so we can't see it when the slope gets too steep. So let's set the slope back to something kind of normal. I'll just go for like a slope of 2. And let's let the y-intercept change now. So now we see some other possibilities for this type of system, right? When we were changing just the slope and we had the y-intercept fixed at something that was kind of inside of the parabola, we had two solutions. But now, again, depending upon where I stop B, here's a great instance where there are, yet again, two solutions. But watch what happens as B goes negative, beyond where the parabola exists graphically. This current snapshot shows actually a situation in which there would be no solution because the linear equation and the parabola don't intersect at all. So that's a possibility, to have no solution. And if I can be really careful with B, there's also a moment, I'm probably not going to be able to show this quite perfectly. There would also be a moment, though, where there would just be one solution. That one's a little harder to see there, but when the linear function just butts up against the parabola at a single point, that's another option. So maybe we should explore just algebraically what this would look like, and then we'll look at something like a circle on the screen as well. So I'll move you guys over to my other screen here for a moment, and we can confirm our algebraic work graphically on Desmos. But here we have a system similar to what I was discussing on Desmos in a more general sense, where we've got a first equation set here, which looks, again, to be like a quadratic, right? We recognize x as being squared, looks like a vertical shift up by 4, so it's just kind of a shift of our base quadratic function. And then the equation beneath that is something linear. So we could solve it for y and feel that y equals mx plus b kind of form to it. So let's talk about an algebraic strategy for solving. Typically what I would recommend is snag the linear equation and solve it for whichever variable in the first equation is not being squared. That would probably be my recommendation. So in the first equation, y is not being squared. So let's solve the second equation for y. And that's pretty easy. It looks like we just need to subtract 6x from both sides. And then anytime you see a y in that first equation, we'll substitute in the equivalent expression, which in this case is negative 6x minus 4. So it definitely still has that same substitution feel that we're used to from the past. So let's make that substitution into the first equation. So the y gets replaced with negative 6x minus 4, and it's still equal to x squared plus 4. And then we need to solve that resulting quadratic equation. So I'll solve this one by setting it equal to 0. So I'm going to add 6x to both sides, add 4 to both sides. And I think, nicely, we're in a situation where this quadratic equation factors. So let's go ahead and solve through factoring. Two numbers that multiply to 8 and add to 6 sound like 2 and 4. So we find either x is equal to -2 or x is equal to -4. And it's easy to want to stop here, but when we solve systems, we really want to obtain a point on the graph. So if we're in a system of two variables, we want to obtain an ordered pair. So that means we ought to go back into the equation where we said y equals -6x minus 4 and plug in those two x's we just found to find the corresponding y. So this is where it's important to make sure you have a proper correspondence of one x solution goes with a particular y, the other x solution goes with another particular y. So if x is equal to -2, we plug in -2 for x into this equation that has y isolated, and looks like we get y would equal to 8. So that means so far one of our solutions as an ordered pair, I'm just going to write it down now so I don't mess it up later, will be -2, 8. So this x goes with this y. So just be really organized with your work. And then same kind of idea to find the other y. We'll plug in -4 back into that substitution equation. So it looks like we'll get 24 minus 4, so sounds like y equals 20 would be the value of y that corresponds with x being -4. So that's our other solution, -4, 20. So like what we were demonstrating in Desmos a moment ago, this looks to be a situation where the linear function cuts the quadratic function twice. So let's check that one out on Desmos. I'll just go ahead and graph that original system to make sure these two solutions that we just found algebraically seem to be valid. All right, here we go. So again, that system originally, I'll go ahead and clear out these guys, was, we'll keep them on and just edit them, how about? Y equals x squared plus 4, and then y, let's enter it just as we got it, which was 6x plus y equals -4. Okay, and again, based on our solutions, we'll zoom a little bit. Let me adjust this. So let's see, our solutions were all the way out to -4. We'll give a little bit of room that way. And then that's pretty good. Let's just peek at it right there. I'll plot our solutions as ordered pairs just so we can really see them falling on the two functions. So there's the solution of -2, 8. That looks good. And then when x is -4, we had found y to be 20. So those look pretty good as our two solutions. These are what we found algebraically, and we're just backing up our work here graphically, might as well. So we got -4, 20 and -2, 8. And those are the two places where the linear and quadratic cross for this system. I'll just zoom out a little bit. Cool. So hopefully that seems good. Maybe before we wrap up this video, I'll just speak briefly to another possible scenario, which has a similar feel to what we just did, and that would be maybe solving with like a circle and a linear, or even a circle and a parabola. So let's say I start off with a circle, and we saw circles a little bit when we wrote our names in Desmos. I'm going to enter a circle with a radius of 6. That is a circle, it's just that my zoom is off. So there we go. That looks more like a circle to us. And then let's intersect it with something linear. How about x plus 6? So as you can see, similar to what we saw with the parabola and the linear function, a circle and a linear function could have two solutions. That's what I just showed so far. They could also have no solution. So I think if I bump this up a little higher, then they never intersect. Or a little harder to show, so I'll add a slider. But if my b value is just so, I can also get one solution. So very similar types of solutions, and the algebraic process would be quite similar as well. Just for fun, let's throw this in as a quadratic instead. And I'll allow for a vertical shift. So this is another scenario of where you're intersecting, right? You could have no solutions to, this one gets a little wonky. Look at this. We could even have 4 solutions if we intersect a circle with a parabola. So kind of fun stuff. I mean, if you look at books on these topics, right, you could have circles intersecting, you could have a circle intersect with an ellipse. So lots of other fun possibilities. If you want to know more, just holler. But hopefully this gives you a nice introduction to solving with nonlinear systems. We'll call it good right there.